Okay, let's dive right into this. Picture this scenario. You are designing a high-precision circuit. You've got your incredibly sensitive signal line, and to protect it from all those nasty stray magnetic fields in your chassis, you wrap it in an expensive, high-quality shield. You do everything by the book. You diligently ground that shield at both ends, expecting total, pristine silence, right? You fire up the power, and instead of silence, your system is just screaming with 60 Hz power line noise. What happened? Why does your premium, perfectly grounded cable act like a wide-open window? It is literally the ultimate engineering irony. You spend top dollar on shielding, only for it to fail completely. This is one of the most frustrating mysteries in electromagnetic compatibility, and trust me, it trips up even seasoned engineers all the time.
So, why do grounded shields fail so spectacularly at low frequencies? Well, to understand why this happens, we have to recognize a fundamental truth. Magnetic shielding isn't some magical, impenetrable force field. It's actually an active electrical process governed by hard math and strict physical limits. By the end of this explainer, you're going to completely master both the intuitive physics and the precise mathematical derivation of what we call the shield cutoff frequency. We're going to break down the exact equations that govern this behavior, map them to a real-world example, and show you exactly how to predict when your shield will act like a solid brick wall and when it'll act like, well, thin air.
To figure out how this happens, we need to look past the macro level and dive straight inside the actual circuit mechanics. When you ground a shield at both ends, you aren't just tying it to 0 volts to drain away charge. You are actually creating a continuous physical loop. In transformer terms, your interfering source acts as the primary winding, and your grounded shield acts exactly like a shorted secondary turn. Think of it like a pair of high-end active noise-canceling headphones. The shield doesn't block the magnetic noise by just being a thick, dense piece of metal. No, it blocks the noise by actively generating an opposing force to crush the interference.
Let's visualize that. When an external magnetic field from some interfering wire sweeps across our cable, it induces a current into our grounded shield. We call this current I sub S. Because the shield is an enclosed loop grounded at both ends, this current flows freely, and as it flows, it generates its own secondary magnetic field. Here is where the magic happens. This secondary field is equal and opposite to the external field inside the cable. It actively cancels out the interfering magnetic flux before it can ever reach your sensitive center conductor. But, and this is a huge but, this active cancellation relies entirely on how easily that current I sub S can flow through the shield.
Okay, let's translate this physical tug-of-war into the actual math. The total noise voltage induced into the center conductor, which we represent as V sub n, is simply V sub 2 minus V sub c. Let's break that down. V sub 2 is the direct induction. That's the raw, aggressive noise voltage the external magnetic field is trying to push into your center wire. V sub c is the cancellation voltage. That's the protective, opposing voltage generated by the induced shield current we just talked about. So if V sub c perfectly matches V sub 2, your total noise, V sub n, drops to absolutely 0. But as you've probably guessed, in the real world that cancellation is rarely perfect.
Let's expand that tug-of-war into its full mathematical form. The total noise voltage, V sub n, equals J times omega times M12 times I1, and then all of that is multiplied by a highly critical bracketed fraction. R sub S over L sub S divided by J omega plus R sub S over L sub S. Stick with me here, this is crucial. The J omega represents the angular frequency. It tells us how fast the noise is alternating. M12 is the mutual inductance between the interfering source and your cable, and I1 is the interfering source current itself. Together, those outside terms, J omega M12 times I1, represent the raw, unshielded noise hitting your cable. The actual shielding magic, that happens inside the brackets. R sub S is the physical electrical resistance of the shield, and L sub S is the inductance of the shield. This bracketed ratio physically dictates whether your shield actively cancels the noise or just lets it pass right on through.
So, the absolute pivot point of this whole equation is that specific ratio, R sub S divided by L sub S. We formally define this as the shield cutoff frequency, or omega sub c. If you want it in plain old Hertz, it's simply the shield resistance divided by 2 pi times the shield inductance. This right here is the mathematical pivot point of your entire cable design. It is the exact threshold where the shield transitions from being a completely useless piece of metal against magnetic fields to suddenly becoming a highly effective active canceller. The lower the physical resistance of your shield, the lower this cutoff frequency becomes, and the wider the range of noise you can successfully block.
Now take a look at how perfectly this graph proves the math we just went through. The dashed straight line represents an unshielded cable. As you can see, the noise voltage just climbs steadily and relentlessly as frequency increases. The solid line, however, is our shielded cable, grounded at both ends. Notice what happens at the extreme left side, at the lowest frequencies. The lines are identical. The shield is doing literally nothing. But right at the vertical dashed line, our cutoff frequency, where omega equals R sub s over L sub s, the shielded curve decisively breaks away and flattens out. That cross-hatched area between the two lines, that is your actual shielding effectiveness kicking in, aggressively locking the noise down to a constant minimum level. Let's make this totally concrete with a real-world engineering walkthrough. Consider a standard off-the-shelf 50-ohm RG58C coaxial cable. The measured shield cutoff frequency, F sub c, for this specific cable is exactly 2.0 kHz. Now, standard rule of thumb, at 5 times that cutoff frequency, which puts us at 10 kHz, the shield is practically fully effective, actively canceling out about 98% of the induced voltage. Keep that 2.0 kHz threshold locked in your mind, because we're going to push some real numbers through our equation to see exactly how this cable behaves out in the wild.
Step 1 of our walkthrough, let's hit our RG58C cable with standard 60 Hz power line noise. Now 60 Hz is tiny compared to our 2000 Hz cutoff. When we plug a tiny frequency, a very small omega, into our noise equation, the j omega in the denominator becomes mathematically insignificant compared to the R sub s over L sub s term. It basically vanishes. So the entire bracketed fraction simplifies to R sub s over L sub s divided by R sub s over L sub s. It just cancels out to 1. Multiply your raw incoming noise by 1, and what do you get? You get the exact raw noise. The math explicitly proves that at 60 Hz, your premium, perfectly grounded shield provides literally zero magnetic field protection. None.
Now step 2, let's contrast that by hitting the exact same cable with 20 kHz switching noise from a nearby power supply. 20 kHz is much larger than our 2 kHz cutoff frequency, so now our frequency, omega, is massive. In our equation, the j omega in the denominator completely overpowers the R sub s over L sub s term. As the frequency climbs, that bracketed fraction shrinks drastically, and the entire equation mathematically limits to a constant minimum. V sub n simply equals M12 times I1 times the constant ratio of R sub s over L sub s. The noise voltage just completely stops rising. The high frequency induced enough current into the shield to activate our noise-canceling transformer effect perfectly.
And this, guys, brings us to the ultimate gotcha in cable routing, the common pitfall that completely ruins so many prototype designs. Engineers often just assume that a shield grounded at both ends is universally protected against everything. It is absolutely not. Grounding at both ends does absolutely nothing against low-frequency magnetic fields. Why? Because at low frequencies, the induced cancellation current simply isn't strong enough to overcome the physical electrical resistance of the shield itself. The current bottlenecks, the secondary canceling field fails to form, and the external magnetic noise cuts right through the cable as if the shield were entirely invisible.
Which brings us to the golden rule of magnetic shielding. To minimize the noise voltage coupled into conductor 2, the shield resistance, R sub s, should be minimized. Because our magnetic shielding relies entirely on induced cancellation current, any resistance flat out kills your protection. This is exactly why a thick, heavy copper braid is vastly superior to a thin aluminum foil shield for low-frequency magnetic noise. Aluminum foil has a much higher physical resistance, which pushes the shield cutoff frequency way up into the audio band, leaving your delicate signals completely vulnerable to lower frequency interference. By the way, it's also why a poor, cold solder joint at your ground termination can completely ruin your entire cable shielding.
Let's do a rapid-fire recap of the exact mechanics we just mastered today. Number 1, magnetic shielding is not passive blocking. It relies entirely on a closed ground loop, allowing an induced current to generate an active, opposing cancellation field. Number 2, because of this strict reliance on current flow, low-frequency magnetic fields will completely bypass standard shields grounded at both ends. And number 3, the fundamental mathematical limit of your cable is the shield cutoff frequency, which is dictated entirely by the ratio of the shield's resistance to its inductance. Lower the resistance, and you lower the cutoff, massively widening your zone of protection. So, I want you to go look at your current schematics right now. Are your cable shields actively canceling magnetic noise, or are their cutoff frequencies sitting way too high, leaving them acting like nothing more than expensive, useless antennas? Remember, it is all in the math. If you want to keep mastering the invisible physics that actually dictate real-world engineering, hit subscribe for more EMC and communication protocol survival guides. Until next time, keep your resistance low and your ground solid.